at MSR. Redmond and Ambuj was also using at the same time. And more recently, we revisited some of the ideas we presented earlier with my student Theodore Marianov and Mike Dinitz, who's a faculty at Hopkins, and with Marianne Mori at Google and NYU. Okay. All right. So the motivation for this work comes from the fact that many real-world problems are posed as sequential decision-making problems. So consider, for instance, time series prediction, or online gaming and auctions, or learning to control. And these applications are naturally modeled as an agent learning to interact with its environment. And online learning is a powerful and popular framework to study these problems of an agent interacting with its environment. Right? However, the typical assumptions we often make in learning, such that the environment is stochastic, IID, or doesn't change between train and test, and stays stationary over time, are often unrealistic to study these problems, to model these problems that we're interested in. Instead, the environment is rightly modeled as perhaps deterministic, non-stochastic, even adaptive to the learner's predictions, and it's often appropriate to model the learner as an adversary who's malicious, knows the player's algorithm, has infinite computational power, and so on. Now, learning in these settings proceeds over a number of rounds, right? And at each round, the player chooses some action from an action set, represented here by these slot machines. And the adversary gets to choose the reward before the game begins, for the sequence of rewards before the game begins for each of these arms. It's often oblivious to the actions of the player. So it's a worst case sequence, but the adversary has already set up the sequence of losses, oblivious to the player's actions. And the player is randomized. At round T, of course, it doesn't get to observe the rewards the adversary has set. It maintains some distribution over different arms, draws an arm from the distribution, and observes the reward for the pulled arm, okay? And only the pulled arm. This is what we refer to as bandit free bet. So it doesn't get to observe the full loss function, but for the reward for the arm that the adversary pulled. And the game goes on. Now, at the end of the game, the learner looks at the rewards accumulated or losses. I'll sometimes refer to these sequences as loss functions or reward sequences, and I'll go there. I'll switch between losses and rewards a bit interchangeably, so excuse me for that. Okay, but let's stick for now with losses. So at the end of the game, the player looks at all the losses it accumulates, and of course wonders how well it did, right? And a natural baseline is to compare with the rewards that it would have accumulated in hindsight if it played a constant arm, right?
Sorry, maybe for this audience you can just say what's the norm.
And this is okay.
So, what's
so that's
different from you?
Sorry?
Just say the standard model and what's the change?
Yeah, so I'm going to just talk about it in a minute. Yeah, I'm just trying to motivate. I know I didn't expect that everyone here would be familiar with regret, but still I think useful to go through this because some of the notation I'm going to introduce would require us to have thought about how the game proceeds in these settings, in oblivious settings. Okay, so formally, this is a setup. So I'm looking at Cain Bandit problem. It's a repeated game between a randomized player and an adversary. Before the game begins, the adversary chooses a sequence of loss functions, FTs, which are maps from the set 1 through k to 0, 1. And during the game, so the player initializes some distribution over these arms. During the game, at each round, it draws according to this distribution, observes the loss FTXT, not the full loss, and updates data T. Right? And much of the magic happens here, the learning happens here in this update. Okay? So this is a standard setup for K-armed bandits against an oblivious adversary. And we can generalize this to arbitrary action sets X, not just K-armed bandit, but general bandits plus oblivious adversary. So we have arbitrary action sets, loss function sets, which map from the action set to 0, 1. And again, before the game, adversary chooses a sequence of loss function, and the game proceeds as we just described. Right? And this, how well the player did is, again, as we discussed, given in terms of player's regret after T rounds. So comparing what the expected cumulative loss was for the player on the sequence of loss functions FTs, given the pool of arms XTs, compared to the best in hindsight, right? So min over C over arms 1 through K of cumulative losses FTC. And we say that sublinear regret, if this quantity is sublinear, then it amounts to learning. Right? And this generalizes various cases that have been studied. So Cain Bandit, as we discussed, but also bandit linear optimization, convex optimization, submodular optimization for different choices of the action set and the loss functions. Okay? Now, in many of the problems that we care about, that I mentioned in the beginning, it's natural to assume that the adversary is actually not oblivious. Adversary adapts or reacts to the actions played by the player or the predictions made by the learner. Okay? So instead of adversary playing loss functions FTs that are maps from X to 0, 1, the adversary is really playing loss functions that map the entire history of the player, so XT to 0, 1. Okay? And we refer to this adversary as an adaptive adversary. So again, the point here being is that adaptive adversary uses the player's past actions, x1 through xt minus 1, to choose FT. Right? And I denote this prefix in red. This is what determines FT. And then the loss that the player incurs at round T is this function FT evaluated at xt. Okay? And this is, again, a natural choice for a large class of learning problems. In fact, anything that's strategic or reactive is adaptive, right? And it's a natural model for online games, auctions, clinical trials, investing in stock market, agents competing with each other, online dating, drug discovery, and many, many other applications in sequential prediction. Okay. Now, we argued some time back, and we were the first one to realize this, but there's a deficiency in trying to understand learning against adaptive adversaries using the notion of regret. Right? So if I use this notation, right, so this is what my loss functions are, and rewrite what the regret is in terms of this notation, then the regret is actually comparing the losses, again accumulated by the player, with competing strategies, again think of this as constant pull of action arm, on the losses that are generated based on player's history. Right? So x1 through xt minus 1 is player's history, and the competing strategy that's being followed is evaluated on the loss functions that are generated in response to the player's actions. Okay? So here is another way to say what I just said in a more pictorial form. So we're going to look at the game tree interpretation of what regret is actually saying. Right? So I'm going to assume that I have 3 actions, so A, B, C, and I'm going to basically look at the game tree where I just show the player's actions for 3 rounds. Let's say the player plays the action C, B, and A. So it starts here at the root, plays the action C, it goes here, and then plays action B, and then plays action A. So it ends up here. So this is the path that the player takes through the game tree. And these are the losses that it observes. These losses were already pre-decided by the adversary. Right? And we compare it with the constant pool of arm, let's say AAA. And a competing strategy starts again at root node, ends up this node, observes this reward, but then we transport it back to the player state. And it pulls A again, and we transport back into the player state and look at the reward that incurred for the next pull of arm A. Right? So this makes no sense, right? So if we were to compare how well a different strategy would do, a constant pull of action would do, then what we really should have compared with the losses that would have incurred along this path. Right? And this is really the point that we wanted to make. Right? A bigger problem, besides interpreting what regret means in adaptive adversary, is that in adaptive cases, learning may not actually give us a sublinear regret bound does not really mean we're learning, right? So in the oblivious case, when these losses do not depend on the player's actions, minimizing regret is equivalent to minimizing expected loss. And this is what we would have wanted to do, but there's no baseline, so we use this as baseline to see how well we did, right? But regardless, minimizing regret is amounts to minimizing expected loss, right? Whereas if you look at the adaptive case, there are really two ways to minimize regret. Right? So I can either minimize my expected loss, which is what I wanted to do, or I could have played a strategy which makes everyone look bad, right? So basically I could either minimize this or maximize this, right? And so what we really need is a notion of regret that takes into account this counterfactual nature of the learning environment here, right? So learning problem here. Right? So what we introduced many years ago now is this notion of policy regret, where we compare the expected cumulative losses with the losses that would have been observed if an alternate strategy would have been followed. Right? And what we're going to focus now is basically on this policy regret, right? in adaptive learning. Okay, so here's the first result. It's a yes. Thanks.
So this quantity can be actually negative.
Yeah, regret can often be negative.
Not in the standard case.
Even in the standard case, it could be negative.
Sorry, so after all that, you're ultimately just saying you're playing the same action?
So we're still playing with this. So this is just for simplicity. I mean, I'm going to talk about competing strategies always as constant pull of the same arm, constant pull of the same arm. This we can often relax. We can allow a competing strategy.
No, you said that makes no sense.
No, what I said was that if I evaluated the constant pull, so if I took minimum over C, where the last action was C, but these FTs, which depended on the player's history, right? So these FTs now are different because they depend on the history of the competing strategy, right? So it's not the same. Right? So I'm denoting them by FTs, which is maybe what is a bit confusing. But these FTs, or if you think of them again, as I said, the FT depends on the first T minus 1 the prefix, and evaluated on xt, right? This ft is different from this ft, if you think of it in that way. This function, right, on the last argument, right, because it depends on the first t minus 1 arguments. That's what I'm saying. So this ft, think of this ft as depending on the first t minus 1 arguments, right? So if I write it that way, then this function would be different from this function. Little c is an action, yes.
But just now you argued that this notion does not make sense.
So I'm saying this notation, to me it makes sense and this is the right way to write it. But another way to think about this is that I could write gt as a function, right? So I can say gt dot is a function which is ft x1 through xt minus 1 dot, right? And if I look at that function gt, and this function gt, these are different, right? So this will be gt, let's say this is gt tilde, right? So the player sees these losses that depend on its actions, and the competing strategy sees functions that depend on its actions. I'm just unrolling it so it's a little bit closer to the way we write regret. But this is very different from regret. So what I said earlier was this is what regret would look like, right? So here's
if the adversary knows that you're going to play the same action at every step, then
there's no way to minimize this.
Sorry?
Yeah, there's no way to minimize this. That's the first result we're going to argue.
So, right.
Yeah. So if you bear with me, that's
because at the very first step they know what.
Yes, exactly. That's exactly where it's.
We can just pass.
Yeah. So we have to constrain them in some way. So that's where I'm heading, right? So there's a very obvious lower bound here that there exists an adversary, there exists a sequence of losses, so that the player's regret is omega t, right? And the construction, as Sanjeev alluded to, is very simple, where we assume that there is some action y in the action set, which is pulled at the first round with some non-zero probability p. Right? And then the adaptive adversary is we can consider a falling adaptive adversary that chooses the first loss function as 0, but every subsequent loss, if the first pulled arm was y, is 1 and 0 otherwise. Right? So it's unforgiving. So if you pull y at the first round, it's just going to punish you forever. Right? And clearly, this happens with probability p, right? So it plays expected cumulative loss against this adversary is pt, Whereas any constant sequence other than y gives a zero loss, right? So the player's policy regret is at least PT, right? So it exists an adversary that learning is not possible with respect to this new measure of policy regret, right? What we can show is that player's standard regret, though, in this setting, if you compute it, is actually 0. And this is what we're trying to basically say. In adaptive adversaries, regret doesn't really mean much. It actually lies to us, right? And I just want to note that this construction is basically based on this assumption that adversary is unforgiving and unforgetful. Unforgetful in the sense that the very first action really sort of kills you if you pull arm Y, and it's unforgiving in the sense that it inflicts endless hurt, endless pain on every subsequent rounds. And what we're going to do for the rest of this talk is first peel away this assumption that it's unforgetful, and then we'll come back in a game setting where we'll assume that the environment or the adversary is actually a strategic opponent, not necessarily a malicious adversary who's out there to hurt you. Okay. All right. So what do I mean by unforgiving? Right? So if you look at oblivious adversary who doesn't react to your past actions, then it's basically just zero memory. It has no memory, right? Whereas an adaptive memory, the way we adaptive adversary, the way we describe it, has infinite memory, right? It remembers all your past actions, right? So a natural restriction to consider is what if we assume an M memory bounded adversary, which only reacts to your last M actions, right? So basically, if the last M actions are the same, then no matter what the rest of the prefix is, no matter what happened before that, these are same loss functions, right? Yes?
I can also think about a different type of adversary that has bounded memory.
Yeah, so this is what we're saying.
Bounded memory and just
no M?
depending on the last time actions are different things. Bounded memory means that I can keep whatever statistics of the infinite past. But
Yes, I see. So it's somehow the influence of the actions farther than M, earlier than M, or much smaller.
decay, yeah.
Maybe decay. Or,
Like bounded memory need not imply decay, right? I can always just remember the
Again,
first action.
So bounded memory allows the previous case. I just remember one case if Y1 was X1 was 1. But you can think about something your new adversarial action depends on something that decays.
yeah, so we have talked about the case where the effect of the path of the older actions decays exponentially, but maybe I'm not sure exactly what's the difference between what you're suggesting memory bounded and what I have here, right? Because I'm assuming the adversaries are M memory bounded, so they only react to your last M actions. Right? That's what I mean. Yes, everyone's okay. So we're going to give a positive result for policy regret against M memory bounded adversary. Right? So let's assume A is some bandit algorithm with standard regret, which is given as OJQ. Q is something between 0 and 1, so something sublinear. Okay. So after J rounds, its regret is sublinear in J. Right? And we're going to denote A as the following map. Given past t-1 observations, losses, maps to the distribution theta t. Right? And we're going to give a very simple reduction, which is simply based on this idea of mini-batching or slowing down learning, if you will, which is as follows. So we're going to construct a learner A tau, which is tau mini-batch version of A for some tau we'll set in a bit. Okay? And what happens is basically it chunks these rounds in rounds of size tau. Right? At the beginning of each round, each batch, we draw action according to the distribution at that mini batch and play that repeatedly for tau rounds. Okay? So this is what we'll say. We construct these mini batches of size tau, and during the mini batch, we just play that constant action that we pulled at the beginning of the batch. And we're going to observe losses for this mini batch and average them and feed it back to the algorithm A. Right? So we're basically constructing a mini batch version of A.
So what is theta J?
So theta is basically your distribution from which you're going to sample the.
By the algorithm.
Yeah. So I'm thinking of A as just a map from past observations to some distribution on the action set, right? So everyone's okay? Okay, so we're going to look at this mini-batch version tau, right? And here's what we're going to argue, that if, as long as these mini-batches are larger than the memory of the memory-bounded adversary, the policy regret of A tau against any M memory-bounded adversary is sublinear in T, okay? And this is how the reasoning goes. For now, let's just assume that the learner knows the memory M. We don't need to. We can.
Can you show the result?
Yes. I'm going to show this again.
Sorry, but I'm missing. Suppose if it's sublinear,
Yes.
J, let's think of Q as half.
Yeah, Q is, let's say, half. You'll get T 2/3 here. So anything between 0 and 1 here will give you something between half and 1 here. Okay. All right. So this is what we're going to assume. For now, for simplicity, assume that the learner knows M, and these mini-batch sizes are larger than M. Right? And we're going to ignore the losses on the rounds where the adversary is reacting. Right? So the first M rounds are in each mini-batch. Basically, in a sense, then construct an oblivious adversary by ignoring the losses in these first M rounds. Right? So we'll average, so we ignore these M rounds, and we average the loss on the remaining tau minus M round for each mini batch, and feed that back to the algorithm A. The number of mini batches here is T over tau. We're paying a constant cost, a unit cost for each of these rounds shown in red, and that's Mj, right? So M rounds for each of the J mini batches, so Mj. And for every, for the remaining rounds, we have this regret, right? So the adversary is not reacting to actions now, right? So we think of this as an oblivious adversary, and we have a bound against an oblivious adversary on standard regret, right? So these are tau minus M rounds, and for each of them, think of this as one round, and we have a regret bound of O to the power JQ, right? And then all that remains is how to pick tau so that we minimize this, and that's what suggested the choice of tau earlier.
So I'm confused. What did you mean when you said that the adversary is not reacting?
So the adversary reacted to these M actions, right? And I can think of the feedback that I observe on the remaining rounds on the mini batch as response from an oblivious adversary, right? So
I'm not sure. So are you assuming that the FTs don't change with, the FTs could still change with T, even though it's feeding in X1, 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 FT need not be the same as FT?
And that's the same case with regret. FTs are different at different times. So on these rounds, if I ignore the feedback on this, right, at this round, every other FT that I look at has the same prefix, right? So they're the same function regardless of what I play from here on. Right? So on these gray rounds, or rounds shown here in gray, it's as if the adversary were oblivious, right? And so I can use the regret bound I have against oblivious adversary. So I can use the standard regret bound.
So even conceptually, I think I'm missing something. Suppose instead of your previous example said, remember the first action and penalize if your first action doesn't.
Yeah.
What if I instead said, look at your last action and I will penalize you for anything, I will penalize you for the last action.
You'll penalize everyone, right? So policy regret could still be sublinear, right? What we showed in that example was that there exist sequences which would necessarily have accumulated loss of 0, right? So the difference is sublinear. But if you come up with such an adversary that's penalizing everyone, right? Or has a constant loss of 1 at each round, sublinear, any measure of performance is 0 or sublinear there, right? It is sort of trivial, I would say.
Like nobody can do any very well against it, right?
If nobody can do very well against which kind of adversary?
The low regret algorithm.
Yes.
Is playing this is compared to this algorithm that plays the same action.
Yes.
And that cannot do well.
In which setting? So here we already have a guarantee, right? So we already begin with the assumption that the algorithm A has a guarantee on regret, right? So on J rounds, if I play
Which adversary?
against an oblivious adversary, the standard notion of regret. Actually, in general, we also have a bound on the regret of the algorithm against an adaptive adversary. Even though it doesn't make sense, we do have those bounds.
But that adversary cannot do well against such an algorithm.
Which adversary cannot do?
Sorry, that algorithm, like the. So that algorithm is just comparing to the algorithm that plays the same action.
Yeah, so we're still playing.
So now this oblivious, this adaptive adversary can penalize that algorithm, right?
This adaptive adversary can penalize, but beyond the third round, it doesn't know what it is playing, right? Whether it's playing.
The nth round?
Yeah, beyond the mth round, right? It has no basis because we're playing the constant action x1, right? It doesn't know our strategy, right? Our strategy is really encoded in first we play x1 for these many rounds, and then we play x2, and then we play x3, right? To the adaptive adversary, we're pretending that our strategy is really constant pool of x1, right? So it's going to on these rounds, right? When we switch from x1 to x2, it's going to hurt us, right? Because we switch from x1 to x2. So one way it could hurt is that every time we switch between actions, it's going to inflict maximal loss on these rounds, right? But by the time we get here, right, all it remembers is these three actions, right? So its strategy is going to be basically geared towards making these constant pulls of arms bad. If it makes all constant pulls of arms bad, then the regret is trivially sublinear, right? So that even if it does that, that's still okay because the regret itself will be sublinear. But what this strategy, mini-batching, allows us basically is that we can explore all such constant pool of arms up to m sizes, right, in this mini-batching fashion, right? And if one of them is good, then we can keep exploiting it. And we don't even have to switch. If x2 were the one constant pool of arm that was going to be good, right, we don't even need to switch on the third round, right? So we just keep playing it. Does that make sense?
I see. So the adversary has the same function, like the last n, and then
Yeah, if you have, yeah.
it doesn't change over time, that function.
That function can change, but it will change for all constant pull of arms of x2, let's say. The function ft can change, but ft at time t for x1, x1, x1 has to be the same, right? No matter what I do next, right? So really, the hand-wavy way of thinking about this, and I mean there are more details, I'm really simplifying things here, is that we really pay a cost for switching, I would say, right? But here I'm simply saying, let's ignore these m rounds, the first m rounds in each mini batch, right? We will just say we'll incur maximal regret for those rounds, right? So this can be at most mj. And for the remaining rounds, right, I'm just going to play as if I'm playing against an oblivious adversary, right? It doesn't react anymore because I'm not changing my strategy anymore as far as he can tell in that round, right? So the regret on these rounds is basically comes from my regret guarantee that I assumed, right? But I do the same thing, right? So they really think of this as being multiplied by tau minus m, right? Because I'm doing the same thing for each of the rounds, right? So my overall Pauli's regret is bounded by mj plus this quantity, and plugging tau that I wrote on the previous slide gives me this upper bound on Pauli's regret.
Is also a lower bound, or you have a better?
So for Cain Bandit, multi-arm bandit problem, we have a matching lower bound. I'm going to show you that in the next. In general, it's not. I mean, for Cain Bandit, it is the case. I'm not sure for other problems if we do get the matching lower bound.
And wouldn't it make more sense if I know that my adversary has a memory of my last m actions to compare against all possible policies which, instead of being C, have, let's say,
So we actually,
a periodic with a period of n.
Yeah. So we extend these results to many such competing classes. So it's constant pull of arm is really a very basic set of competing strategies. It's easier for presentation. I know it's not satisfactory in many ways when you think about it. We do extend these results to strategies where you are allowed to switch, but not by too many. So it's a sum bound. You can have as many as S switches over T rounds. We also compare this with other notions. So we extend the policy regret to policy swap regret. So where, in hindsight, if you switch every action with any other action, what would the regret be? And so there are many other competing strategies that we consider in the paper. Here, for simplicity of presentation, I'm just looking at the constant pull. But those are really tricks that we also apply in standard regret. So all of those tricks apply here also. There's nothing new going on there. There's very standard extension. So, other questions? Okay. And a key takeaway here really is that every time we switch, we're paying a cost. Right? And this is the equivalent view I will take in when I try to extend these ideas to other settings. Okay. All right. So here's a main result. Again, if you have a regret of standard regret against an oblivious adversary of T to OTQ, then you get policy regret, which is OT1 over T minus Q. Right? And again, we can extend this policy regret to various standard settings. In multi-armed bandit, square root 2 regret translates to T 2/3 policy regret. And similarly for other settings. For multi-armed bandit problem, this was shown later that this is actually minimax. So they are matching lower bounds. Okay? We'll revisit this question of can we improve this if we make additional assumptions, because in multi-armed bandit setting, one of the problems we're really interested in, the action set size can be very large. Okay? So we'll revisit this question. Okay, let me say a bit about some related work. We were not the first ones to realize that the deficiencies in interpreting regret in adaptive settings. Mehrav et al. Considered this problem of notion of policy regret. They consider memory bounded losses. They give regret bound O2 2/3, but they consider expert settings, so full information settings, so which would be a special case of what we're doing here. There are other works, most notably by D. Farias and Megiddo in 2006. They also recognize that the regret is inadequate, completely forsake the notion of regret, and then they make strong assumptions about losses, how they drift and how they evolve. Another work was by Rabko and Herter, which generally looked at the question of learnability in reactive environments with arbitrary dependence. They have high-level similarity with the kind of things we're talking about, but they focus on stochastic setting. They looked at only asymptotic bounds and gave an algorithm that was intractable. Okay, I'm going to switch gears now and basically come back to the question that I was posing. This was an aside, whether we can improve on this if we assume something else about our learning problem. Right? And in particular, what I'm going to assume is what if there's partial feedback. So we're not completing bandit setting, but there's some graph-based feedback. And this, again, is a natural setup for many real-world problems, where we, when pull an arm, we also see reward or losses for some related arms. Right? So basically, what I'm saying is that certain semantic actions and connections in action spaces which create observability dependencies of corresponding gains and losses. And we're going to model this in terms of an undirected feedback graph. Right? So again, the idea here is that if you're interested in digital cameras and you'll click on an ad for digital camera, then maybe you would have clicked for an ad for digital camera for a different brand, or maybe also clicked an ad for accessories of digital cameras. Right? And we're going to basically model these as in terms of an undirected feedback graph. Here again, each action corresponds to a node. And if there's an edge between two nodes, that means these actions, the losses for action 1 reveals the loss for action 2 if it is adjacent. Okay. And this specializes full observation and bandit feedback, right? So full observation would be fully connected graph. Bandit feedback would be graph with no edges. And in general, we'll be basically interested in what property of a general partial feedback graph determines the minimax regret bounds here. So again, each node is associated with an action. We observe losses for all nodes connected to the selected action. And we're going to, in particular, look at this notion of counterfactual feedback, where each node is an M tuple, right? So we're, again, considering M memory-bounded adversaries. So every node here is an M tuple of actions in the action set V. I'm going to denote it by V from here on. And the motivation is, again, as I said earlier on the previous slide, but I'm going to repeat it. So in many settings, for example, in healthcare, similar patients, when they're prescribed different treatments, reveal counterfactual feedback about each other. Right? And the question we're going to look at is basically, can we improve on the policy regret bound that we get from previous results, which has dependence of 1/3, or dependence on the size of the action size set as 1/3, and dependence on the number of rounds as 2/3. Okay. So this is what I said on one of the previous slides, that we can equivalently think of the mini-batching reduction as minimizing regret with switching costs associated with it. Okay? So in each mini-batch, we repeat a fixed action, right? And if we switch from switch between mini batches, so if we switch from X1 through X2, we necessarily pay a price for switching. Right? If I didn't switch from X1 through X2, I won't have to pay a price for these rounds shown in M. Right? So I can think of mini batching reduction equivalently in terms of minimizing regret with the switching cost. Every time I switch between actions, xj minus 1 xj, I pay some constant cost. Okay, so this is what I'm going to formally describe the problem. So again, the standard setup is as follows. You have an adversary and a player, you're minimizing regret, and in multi-arm bandit setting, the standard bound, which is minimax regret, is square root vt, right? So v is again the action set size, so think of kt. When we add switching costs, right, this is the problem we're interested in, right? So we want to minimize the regret, which is basically looking at the regret plus switching costs associated with every subsequent round where we switch. And just based on the discussion that we had, because the regret with switching cost is equivalent to policy regret, what we have here is that the regret, minimax bound on the regret here is v to the 1/3 to the 2/3, right? And there's a big gap here, right? So in completely bandit setting, we get square root vt. And again, in bandit setting, where we have switching cost, we get v to the 1/3 and t to the 2/3. Right? And the question we want to understand is, can we bridge these two regimes? Okay? Of course, without assuming anything else, because these are minimax regret bounds. And so the additional twist we have on the problem is that what if there's an additional feedback, partial feedback available in form of feedback graph? Can we do better? Okay. So our first result is that in terms of the number of rounds, we can't. So there is, again, a construction which goes as follows. So imagine you have 3 arms, and this is the feedback graph you have. So V3 is a revealing arm, which if you pull, reveals losses also for V1 and V2. Okay? And we set the sequence of losses as follows. So V3 incurs a constant loss, a unit loss, the maximal loss possible. Okay? But it reveals information about V1 and V2, right? So we can explore if we pull V3, but we'll pay a lot in terms of instantaneous regret for pulling V3. Okay? The loss of V1 and V2 we set are according to a random walk, which is carefully designed, and we pick in the beginning at random which one is better. Right? So V1, for example, is better perhaps than V2 by a small constant epsilon. Okay? And the way the random walk is constructed is that in order to distinguish between which arm is better, V1 and V2, we either switch between V1 and V2, okay, or we keep pulling V3. And what we can show is that you really have to pull V3 at least t to the 3rd times, or switch between V1 and V2 t to the 2/3 times. Right? So in either case, the regret is at least t to the 2/3. So the lower bound here cannot be improved in terms of the dependence on t. Right? So the t to third is the switching cost we'll have to pay. Okay. So the question that remains, can we improve the dependence then on the size of the action set, right? V to the 1/3. Okay? And here we can actually show a positive result, and I'm going to motivate the idea here by looking at a very simple feedback graph, that is a star graph, right? So where there's a single revealing arm, or, which I'll call or, denoted here in red, which if pulled, gives me information about everyone else. It's almost as if I'm the full information setting. Right? Again, here are two ways to explore. Right? So we can explore by pulling or we can switch between non-revealing arms. Right? Now, if or is good, if the revealing arm is good, then I'm simultaneously getting to explore and incur small regret. Right? So I pull or, I instantaneous regret is small, but I also get to observe everything else. If or is poor, though, then we need to somehow understand what's the trade-off between exploration and exploitation. So we have to we can explore through or, but we'll incur some regret. Right? What we can show at first is that if there's a fixed mini-batch like we did for the problem earlier, then the exploration is costly. We will actually, all we can show is the regret bound is 1/3 dependence on V. Right? So what we propose is the following adaptive mini-batching strategy, where the size of each mini-batch is proportional to how good the revealing arm is. Right? So instead of having a fixed mini-batch size, the size of the mini-batch at round j corresponds to how good, what is the probability, according to the distribution that we're maintaining, of pulling arm, the revealing arm or at round j. Right? And times tau. So there's some maximum mini-batch size that we can achieve. So the key idea here is that we'll use an adaptive mini-batch where size of the mini-batch is proportional to the payoff that we observe from the arm that reveals losses for everything. At the same time, we disallow switching between non-revealing arms because they don't really reveal loss about each other, and there's a switching cost associated with them. So what we can show is that for this adaptive mini-batching strategy, we can get regret bound, which is t to thirds, and has no dependence on the size of the action set. So it's just 1, right? Instead of in this case the size of so instead of paying a cost which is proportional to the size of the action set, we don't pay any cost. Okay. What about the general graphs? So not all graphs are star graphs. What about general graphs? Well, the idea here is again very similar. We take any general graph and we decompose it into a bunch of star graphs. Right? And for each of the star graphs, we play the adaptive mini-batching according to the payoff of the revealing arms. So there are 3 revealing arms in here, and we disallow again switching between non-revealing arms. And the question that remains is, so how many star graphs can we get from any general graph? And the smallest number of star graphs that we can decompose a given graph into is known as the domination number. And the number, these vertices shown here in red, is dominating set. So the domination number of a graph plays a fundamental role here. What we can show is that the regret of this adaptive mini-batching strategy yields a regret bound, which is dependent on the domination number of the graph to the power 1/3 t to the 2/3. And note that this can be much smaller than the number of actions, right? So here are some examples to motivate what domination number is. Dominating set for a graph is basically a subset of vertices such that every vertex is the smallest subset of vertices, so that every vertex that is not in that subset has an edge with one of the vertices in the set. Right? That's a different way of describing what domination number is, right? So for fully connected feedback graph, the domination number is 1. So we recover the bound that we know from expert setting. For a bandit set, there is nothing we can do better. So we do pay a price proportional to k, which is what our minimax regret bound also showed. For star graph, the gamma g is 1, which is what we showed on the previous slide for the star graph. And in general, the Domination number is the price that determines the minimax regret in these settings. Right? It's always smaller than the size of the graph, and in many cases, such as fully connected feedback graph or this general arbitrary graph or star graph, it can be substantially smaller than the number of vertices in the graph.
But you can sort of continue the game, right? Like if the dominating set is too large.
Yes.
The adversary cannot, rely on all the
Yeah, it can not rely on all
the neighboring information.
If the domination number is large, it cannot rely on.
Wait, does that mean the degree is large? It is.
Domination number does not imply the degree is large. So there are two ways to think about the domination number. One is, let's say I have a general graph. What is the smallest number of star graphs I can decompose it into? Another way to think about this is a subset of my vertices on the graph, such that the vertices that are not in the graph have an edge, are adjacent to at least one of the vertices in the subset. And this is really about the feedback that the player gets. The adversary doesn't get to control the feedback graph. There could be settings where the adversary also gets to control the feedback graph, and there then you can construct adversaries which could try to construct different feedback graphs at each round, which are somehow hurting the performance of the learner. Okay, and we can construct settings. We can give lower bounds, which basically I'm going to skip this over, but say that this dependence on the domination number is optimal. And so we have lower bounds which match the upper bounds achieved by this adaptive mini-batching strategy. Okay? And again, because of this reduction that I discussed from mini-batching to switching cost, what we can show is that the minimax policy regret given a feedback graph is gamma g to the 1/3, where gamma is the domination number, t to the 2/3. Yeah? All right, questions? Before I switch? I don't have much time, so I'm just going to quickly go through what else did I have to say. So again, I said the construction, the lower bound construction that we had in the beginning assumed that the adversary was unforgetful and unforgiving. And we made an assumption on what happens if the adversary is memory bounded. How can we design sublinear policy regret algorithms? What we're going to assume here is that the adversary, the learning environment, is not necessarily malicious, but an opponent, strategic opponent. Right? So we're going to basically look at what happens if in a game each player is minimizing its policy regret. How can we describe the behavior of the game? Okay, and I'm going to skip over some of the details here. And I'd simply get to the key questions and then the main results, right? So one of the questions which actually motivated this work was that there's this hierarchy of equilibria, right? And many of these or either do not exist or hard to compute, and the ones that really are easy to compute and learn are this class of coarse correlated equilibria, which can be achieved if each player in a game plays according to an algorithm which guarantees that each player will have no external regret, will have zero regret, right? And policy regret is a bit different. And if you think about this, policy regret is somewhat natural to consider in games. If you're in a game, rather than just minimize your regret, assuming that other players are oblivious to what you're doing, the natural assumption is that if you play a strategy, then other players will adapt to your strategy. Right? And so what you should do is really minimize policy regret. And the question we want to understand here was what happens, how can we describe the behavior of the game, either in welfare or in terms of this equilibrium, what happens when the players in a game minimize their policy regret. Right? Arguably, policy regret is a stronger notion, so maybe it implies small regret. So maybe what we get is indeed, again, a coarse-correlated equilibrium. Okay? So our first result that we have is that there are actually somewhat incompatible. There exist sequences of loss functions for which the player can either have zero policy regret or zero external regret. It cannot have both be small for that given sequence of loss functions. And so they are somewhat incompatible. So it becomes interesting then to understand how is policy equilibrium compared to this coarse correlated equilibrium. Okay?
No, but those amounts are different, right? Why is it?
So actually,
Two numbers are different.
no, one is linear actually. We can show that if the policy regret is sublinear, then the external regret will necessarily be linear and vice versa. So you either mean, yeah, so there are sequences where you can only have sublinear policy regret or sublinear external regret, but not both. Okay, and so again, to remind you what an equilibrium is in standard in games where each player is minimizing their regret, it's basically special solutions to the game where such that there is no incentive for either player to deviate from the strategy given by their respective algorithms to deviate, right, from the strategy. Okay? And again, if all players have sublinear regret, they play according to a zero regret algorithm, then the average play converges to a coarse correlated equilibrium. That's a well-known result. And what we want to understand here is that what happens if all players have sublinear policy regret? What kind of equilibrium do we converge to, if any? With the motivation being that if there is a nice characterization of the policy equilibrium here, then it would describe the solutions in a more elegant manner, in the sense that I could argue that even if I deviate from my strategy and take into account how the opponent would deviate or react to my deviation, there's no reason, no incentive for me to deviate, right? So it would be much stronger characterization of the behavior of the game. So I'm going to skip some of these details on how we actually address this. The key results or takeaways are as follows. So one is that if the players in a game play according to a stable, no external regret algorithm, where stability here means that if I change past M actions to something else, then the distribution on the action space doesn't change by too much, captured here in ST. Right? So if players play according to some stable algorithm and achieve no regret, then they also achieve sublinear policy regret. So in general, it's not true, as we argued on when we discussed the incompatibility of regret and policy regret. But if they're playing according to a stable algorithm, then regret implies sublinear regret implies sublinear policy regret. Furthermore, now that if each player does play according to a stable no regret algorithm, achieves a sublinear policy regret, then what we can show is that the no policy regret play converges to the set of policy equilibria. Where again, as I said earlier, the policy regret equilibria are special solutions to are distributions over strategies of the players, such that if a player deviates from its strategy by playing a different action or different strategy, and takes into account also how the other player would react, there's no incentive for it to deviate. Okay? Finally, we want to resolve what is this relationship between coarse correlated equilibria and policy equilibria. So the first result in terms of understanding this hierarchy or nesting is that stability plus no regret implies policy regrets, therefore sublinear policy regret, therefore coarse correlated equilibrias are contained within the policy equilibria. But there is again an incompatibility result, which is basically saying that there exists policy equilibrium which cannot be achieved by any set of players minimizing their external regret, so which is not a coarse correlated equilibrium. So the nesting that we propose, which we argue, the nesting that we argue is that CCs are contained with policy equilibrium. Policy equilibrium is a richer class of descriptions of games in two-player settings. Okay, so to summarize, what we've seen today is that sublinear regret is not very useful in adaptive learning algorithms, right? It's hard to interpret. In fact, it's a bigger problem. You can achieve sublinear regret by by hurting everyone, by actually exploring the space of the learning environment where every strategy is bad. Whereas simple mini-matching yields algorithms which guarantee sublinear policy grid. Furthermore, if we do adaptive mini-batching, it gives us optimal trade-off between exploration and exploitation when we also consider feedback graphs. And the policy grid with counterfactual feedback graph, the minimax regret is given in terms of the domination number of the graph to the 1/3 and t to the 2/3. Finally, in game settings, we argue that the no policy regret play is a natural notion. We should always take into account how the adversary will, or the opponent will react if we deviate from our strategy. And it generalizes coarse correlative equilibrium. Some ongoing work and future directions, as I said earlier, the way we model unforgiving adversaries as strategic opponents is fairly mild. What we really want to do here is characterizing the forgiving nature of adversaries or learning environments in terms of how the losses drift, in terms of bounded drift of losses, or maybe exponential decay in terms of the memory. Another direction that we are pursuing currently is, can we learn a deterministic MDP for now, deterministic for now, if the rewards corresponding to the action I take in a state are controlled by an adversary, they're non-stochastic. And this will help us extend some of these algorithmic ideas to reinforcement learning, where we would have multiple strategies, multiple policies being explored at the same time. And the key innovation that would be needed is, how do we learn with a band of bandits, right? So we can think of this as a model selection problem, where we have multiple algorithms designed for different environments in reactive settings. And what we want to do is, we want to learn as well as any best strategy in hindsight. And this is natural applications to reinforcement learning. And finally, we are trying to understand the training of GANs in terms of the policy equilibrium that we just described here. Because again, we can think of GAN as a two-player game. And many optimization problems can be described in terms of policy equilibrium. And so what we hope to do is try to understand the training of GAN in terms of this policy equilibrium. Okay, so that's all I have. These are some of the key references that I had, and I can take more questions.